Thank you for holding. This is the operator. We will begin the conference call shortly. Again, thank you for holding. This is the operator. We will begin the conference call shortly. Thank you for holding. This is the operator. We will begin the conference call shortly. Again, this is the operator. We will begin the conference call shortly. Thank you. Good afternoon, and thank you for standing by. I'd like to inform all participants that your lines have been placed on a listen-only mode until the question and answer session of today's call. Today's call is also being recorded. If anyone has any objections, you may disconnect at this time. I would now like to turn the call over to Mr. Josh Finch. Thank you. You may begin.
Good afternoon, and thank you for joining us today. Sorry for getting a little bit of a late start. I'm Josh Finch with NASA's Office of Communications. We're here to discuss preparations ahead of NASA's SpaceX Crew-4 mission to the International Space Station as a part of the agency's Commercial Crew program. The Crew-4 flight will carry astronauts Kjell Lindgren, Robert Hines, Jessica Watkins, along with ESA astronaut Samantha Cristoforetti. Here to talk more about Crew-4 preparations, I'm joined by Captain Leaders, Associate Administrator for Space Operations Mission Directorate at NASA Headquarters, Steve Stitch, Manager of NASA's Commercial Crew Program at Kennedy, Joel Montalbano, Manager of the International Space Station Program at NASA's Johnson Space Center, and William Gerstenmaier, Vice President of Build and Flight Reliability at SpaceX. We're going to begin with opening comments from each of our presenters, and then we'll take your questions. To get into the queue, please press *1 on your phone. And with that, we'll go to Kathy.
So first, I'd really like to thank everybody for being here today and getting on the phone so quickly to allow us to talk about our work and all the preparations that we're doing to get ready for our SpaceX Crew-4 mission to the International Space Station. As you know, this is another big year for the agency, and we've got a ton of important missions in the near future, which include Artemis 1, commercial crew and cargo flights, and our first private astronaut mission to the station and even more science missions. But like we've talked about numerous times before, as we're moving on to our crew cadence, it's really critical that we stay focused and carefully execute all of our missions, especially as we are getting ready to test and fly the systems that will be flying our most precious cargo, our crew members. So, we continue to learn and benefit with Commercial Crew from our commercial cargo missions and our Falcon 9 and Dragon Insight. And as we are following along, we are always, getting a lot of data and making a concerted effort to make sure that we are using that to be able to continue to follow the hardware and hear what the hardware is telling us so that we can continue to learn and fly our folks safely. And so we wanted to make sure that we got together today to kind of give you a sense of the last progress. I understand there's been a lot of interest after the last cargo flight. I wanted to explain a little bit about the difference between our crew and cargo coverage. We obviously, crew flights have a lot of focus, and we do the live coverage for both launch and on-orbit operations and reentry. With cargo, we have been backing off on doing the live coverage of that. Obviously, we're doing space station coverage, and we give you inputs, but we haven't been doing live coverage just from not deploying the assets and just the cost of doing those operations. But with the interest that we've had in the cargo vehicles, what we'll start doing is kind of doing a media telecon like this after the flight, so that if there's any questions that you have about the mission or the conducting of the mission, or we love it just because we could talk more about what happened on the mission and what came back, we'll make sure that we do that in the future. We obviously want to make sure that these are the nation's missions, and we want to make sure that you're understanding that we're providing the data that we need to be able to make sure that our nation understands what's going on their missions. And with that, I'd like to hand it over to Steve.
Yeah, thanks, Kathy. It's a pleasure to be here today to share a little bit about the progress toward the next crew rotation. This will be our third crew rotation coming up here in the spring. Safely launching Crew-4 and getting the Crew-3 crew home is our highest priority in CCP. We're currently tracking Crew-4 to a launch date of 4/15. The hardware is looking really good for that flight right now, and as it goes through processing. This will be a direct handover this time, so Mark Vandehei will return before the flight, and so we're planning on a direct handover from Crew-4 to Crew-3. For this flight, it's the first time we will have reused a Falcon 9 booster that's flown 3 subsequent times. For Crew, SpaceX has flown many flights with higher life boosters, but we're working through that first-time reuse of a 4-flight booster for us and the team. Both the SpaceX and NASA teams are doing a great job working through the data for that and getting that additional work done behind us for the flight. We will have a brand new Dragon capsule on this flight. It'll be the first flight of that spacecraft. That spacecraft production is at Hawthorne right now. I had the pleasure of being out there earlier this week and seeing that vehicle as it goes through its final preparations for flight. It was looking really good. You know, we've been embarking upon reuse for the crewed missions, and we've been methodically working through that many times, flying hardware on a cargo vehicle first. For this crewed flight, we're going to reuse the heat shield structure, not the TPS material, but the structure for the first time on a crewed vehicle, and SpaceX has done that a few times on cargo, which is really the benefit of the cargo program. We can see things fly on that vehicle for the first time in either whether it be new hardware or reuse, and then since the vehicles are very common, we can take that data and use it for Crew. You know, we continue to look at all the flights of Dragon. SpaceX is a great partner in terms of sharing data on not only the cargo vehicles, but all their missions. We did see on the CRS-24 mission, one of the 4 main parachutes lagged a little behind the other 3 in terms of deployment. This was a little less than we saw on the Crew-2 vehicle. You know, on Crew-2 return, we had one that was about a 70-second lagger. The descent rate on the cargo vehicle was well within family, even with that lagging parachute. We are working with SpaceX to go through and look at all the data from that CRS-24 flight. We do our standard post-flight process, which we look at all the imagery. In fact, NASA flew the WB-57 to obtain imagery as well, in addition to imagery on board. We will go out and also inspect those parachutes. All 4 mains were recovered, in addition to the 2 drogues. We'll go out with the SpaceX team, our parachute team in the commercial crew program will go out and look at those parachutes and see if there's anything anomalous with those. We'll take the time to look through the data for this and make sure that we can clear it before both Crew-3 return and Crew-4 launch. You know, Crew-3 is doing well in orbit. That spacecraft is performing really well. We do a weekly checkout, and the systems have been doing phenomenally well. The crew's doing great, and that vehicle remains healthy, and so we're very excited. It's about halfway through its increment, and looking forward to a return in late April. And with that, I'll hand it over to Joel.
Thank you, Steve, and thank you, Kathy, and thank you guys for dialing in today. It's always good to talk. You know, our highest priority remains continuing the safe launch and return of both crew and cargo missions, and it's necessary that we do this to maximize the return of the International Space Station. From a coordination standpoint, Steve and I are tied together at the hip. You know, our technical specialists on the space station side are tied into the same technical reviews and the boards that are going on in the commercial crew program. You know, we work as one integrated system, and it's important not only for the International Space Station, it's important on the fact that we represent the international partners, and we're invested in working with them to make sure that we do this safely for their crew, for their research, and the hardware on these flights. SpaceX 24 returned just under 5,000 pounds of scientific experiments and station hardware. And our ability to return this equipment and science from the International Space Station is critical for us as we move forward, as we learn, and it's going to play forward into the Moon and into Mars program, because we're doing things on board Space Station today that are going to help us as we move forward in the future. The steady cadence of the crew and cargo missions help us make this the decade of results that you've heard so much that we're celebrating now with the fact that we have commitment to go to 2030. It's important that we be very clear and illustrate what we're doing on board Space Station and show everybody that what the benefits of this great space station brings. Besides the Crew-4 and Crew-3 work that Steve talked about, we continue to have other missions, and ISS continues to be hopping. You know, with Progress, we have a Progress launch in mid-February, February 15th, followed shortly thereafter by Northrop Grumman, their 17th resupply mission scheduled for the 19th of February. The Axiom 1 mission that Kathy mentioned, we're targeting that for March 30th. And so that'll be the same day that the Soyuz lands. They'll land about 9 hours before the launch time of the Axiom 1 mission. Move forward, you got the Crew-4, OFT-2, SpaceX 25, and then there's a number of EVAs that we're planning as well. We are looking forward to Mark Vande Hei returning at the end of March. Once he returns, he will have 355 days on orbit. In fact, just yesterday was his 300th day on orbit. And so Mark is doing awesome. You know, it's just a pleasure to have Mark on board, and we're looking forward to him to setting the new record when he lands on March 30th. As far as coordination with our Russian colleagues, we are continuing the work, the crew swap agreements. We have astronauts training for the Soyuz mission in the fall, as well as cosmonauts training for the SpaceX mission in the fall. And we're still working with all the government agreements, but in parallel, we are working at the operational and training level to make that happen, and we're excited to look forward to that in the fall. With that, let me hand it over to Mr. Gerstenmaier. Thank you.
Yeah, thanks, Joel, Steve, and Kathy. Again, here at SpaceX, we're getting the capsule ready to go fly here. It's in the clean room. It's kind of going through kind of the final integration stuff, and it looks like it's in pretty good shape for Crew-4. We're working through all that activity. We also have the stage 2 that will go along with that capsule. That's also being worked here in Hawthorne, and that activity is progressing very well. We have the booster that the teams talked about. It's down at the Kennedy Space Center. It's in a transfer aisle. We really haven't started working on it yet, but we've laid out all the work that needs to be done on that booster to get it ready to go fly. We'll coordinate all that activity with NASA. And again, I think the beauty of this overall activity is we're getting lots of flights. We're getting a lot of chances to see hardware, getting a lot of chances to learn things and see how the hardware actually operates. You know, we do our best to design and test and put hardware together, but then when we actually see that hardware fly and we get real results back, that really informs what we're doing. And if we continue to do that, we'll learn from that activity and actually make us safer to go fly in the future. So this kind of continually learning and continuing process of looking at the data, understanding what we're seeing, using NASA assets wherever we can. When we do even one of our private missions, we'll have the NASA team come and they'll do and watch activities with us so they can actually see what's going on. So we use them as we do like parachute loading. They'll actually monitor that parachute loading as we put those parachutes on even one of our private missions. We use the NASA aircraft on our private missions to actually monitor for chute performance. So this works out to be a really good relationship with this back and forth. So we use all these flights, cargo, crew, private missions, all to continue to add to the data set to make sure that we're safe to fly and ready to go fly in the future.
Thank you, Mr. Gerstenmaier. We'll now turn it over to take your questions. As a reminder, please press *1 to get into the queue, and to ensure as many people get a question as possible, we ask you to limit to one question, and then we can come back around if we have additional time. And our first question will go to Jeff Faust at Space News.
And if this is a new phenomenon, is there any changes in construction, operations as such that might explain why that lagging parachute is taking place now and not before? Thank you.
Hey, Jeff, this is Josh. I think your first part of your question was cut off, so if you wouldn't mind repeating it. Thank you.
Sure. I was asking if you'd seen this lagging parachute on any other missions beyond CRS-24 and Crew-2. Thanks.
Yeah, I can start off. This is Steve Stitch, and then see if Mr. Gerstenmaier has any comments as well. You know, this lagging parachute phenomenon is something that we see with these large ring cell parachutes, and so we have actually seen it in other tests and other CRS flights as well. So it's just what we think, and this is just a theory at this point, is aerodynamically the three of the canopies may sort of shade, if you will, one of the other canopies, and then it just struggles to inflate at times. So that's sort of the working theory, but we have seen it in other flights. It is interesting to us that it's we saw it on two back-to-back missions, right? A Crew-2 return and now CRS-24. So we're taking the extra time to continue to look at the system. We'll go through all the imagery. We'll inspect the parachutes. So far we don't see anything that looks strange in any of the imagery or off nominal. We'll go look at all the build paper for the parachutes and the way they were rigged and packed. We have not changed anything on the parachute system since really we started flying these parachutes on the Demo 2 flight.
Yeah, again, from a SpaceX perspective, we saw some of this lagging performance on some developmental chutes previously. These are the Mark III chutes. We made no major changes to the hardware or the design systems. As Steve described, we think this is just a feature of the way the 4-chute design works. If you look at the actual data, you wouldn't even detect the fact that these chutes we saw on Crew-2 and on CRS-24 were actually late. If you look at the descent data, it looks just like a regular 4-chute parachute return. So what we're trying to understand is there anything here that relates, that could be a cause between the two? Is there something that has changed? So we're working with NASA to dig in all the data, look at all the information and see if there's anything that causes a concern one way or the other. But again, I think this is just a normal thing that we're learning, and we take advantage of the data we get on each one of these flights. And can it teach us something, or can we learn something from this that actually helps make us better and safer for the future? So we're not taking anything for granted. We see this. We don't think there's anything that's different than we saw in the developmental world, but we'll spend the next couple of weeks as we head up to the flight readiness review making sure that we didn't miss anything.
And our next question is from Irene Klotz at Aviation Week.
I'm not sure who this question is for, but basically, could you just describe what you're going to need to do to actually clear this issue ahead of the Crew-4 flight, or I guess for GERS, possibly even ahead of the Axiom flight? And for Kathy, thank you for the agreeing to the future press briefings following the CRS landings. And I don't know if there's anything you might want to add about why this information wasn't put out in the status report following the CRS-24 splashdown. Thanks.
I'll start off in talking about what we need to do in preparation for the flight readiness review process for Crew-3 landing and the Crew-4 launch. You know, what our teams are going to basically do is go through and look at all the imagery data first, and do we see anything off nominal in the imagery that would suggest there's something off nominal with any of the canopies? Did something hang up where it shouldn't have? We'll go look at all that data and make sure that it's just as we expect it to perform. We'll go inspect the canopies at the vendor with SpaceX and lay them out and look and see if there's anything there that looked off nominal. And then we'll do an inflation analysis to make sure all the parameters on CRS-24 were within what they were expected to be. If all that is very much nominal, then I suspect we'll clear this and then be ready to go fly Crew-4 and Crew-3 return. We just want to take, as Gers said, a little extra time. You know, when something happens like this a couple times in a row, although we have seen it in other parachutes, including the Mark II parachutes also that SpaceX has flown for CRS, and we did some development testing in commercial crew with, had this same phenomenon, which is a large ring cell parachute, but very similar design. We want to just make sure that we take extra caution with this very critical system. And I'll see if Bill has any comments.
Yeah, what we'll do is, if you remember when we had the Crew-2 late deploy, we did quite a bit of work before we went to Crew-3. If you remember, we helicoptered those parachutes back from the recovery area, that one parachute that was slow to deploy, and we actually hung it in Area 59 down at the Cape. We actually brought the NASA team in and the airborne team in to go look at that hardware. So the things we look at is, there's some reefing line cutters. These parachutes, they deploy in stages where they're reefed together. They take some loading, then we go to stage 1, then we go to stage 2. So these reefing line cutters, we want to make sure there's 2 different timings on those. We need to make sure that the proper cutters are installed in the proper location on the line. We'll also go take a look at the line to make sure that the cut through the line is clean and crisp, that there wasn't a hang up there where the cutter didn't work exactly right. So we'll go look at that. We'll go look at the riser material. We'll go look at the porosity of the canopy to make sure it's okay. All those things that we did back on Crew-2, we'll do all that with the hardware that we got back on CRS-24. The good thing is we got all 4 chutes back. We got main chutes back. We got the 2 drones back. We got all the hardware. We'll go through it methodically with the teams. We'll make sure that we're really comfortable before we go fly. We'll do the same thing before we go fly Axiom. So we will have cleared this through the SpaceX activities and processes here to make sure we're really got a good configuration and we didn't learn anything that calls into question our basic certification and operation of these parachutes. If we do, we'll work with NASA. They'll be with us hand in hand, but we'll use the Axiom kind of as our guide, and then we'll get to do a bigger review with NASA as we get to the flight readiness review process for Crew-4. But this will be thoroughly investigated, very similar to what we did in a pretty expedited manner after Crew-2. But we'll use this as another data point and see if we can actually get smarter about how these systems operate, so we can make sure that yes, this really is a nominal operation of this 4-chute system. Or maybe there's something here that's going on that's different. So this is, again, being curious, being hungry, my words, to make sure that we're getting the most out of these flights. And it's really great that we can fly and get this data and learn how these systems operate. This flight data is tremendously precious to us, so we want to get the most out of the investigation by looking at the parachutes and understanding how they operate and how they function.
So, Irene, let me kind of answer your last question. I think just as we're learning about how we fly, there wasn't any anomalous, let me get that word out, anomalous loading data. And so, yes, this was an area of interest for us, but we're learning. We right now don't know if this is a feature, and we kind of have the same discussion at our FRR for Crew-3, right? It's and really with the work that we're doing, we're kind of trying to hone in on that. It's why we've decided to go more to the press conference approach, because we feel like, or not the press conference, but this telemedia conference, because we feel like this was a fairly easy way for us to have this kind of a nuanced conversation. Sometimes a blog post isn't as easy to have that nuanced conversation, even though we obviously are still trying to convey data. I don't know. So we're trying different approaches, and we're trying this, and we'll do the teleconferences after the cargo discussions, and we'll continue to work together on what's the best way to convey the data as accurately as possible, right?
Thank you.
And our next question is from Bill Harwood at CBS News.
Hey, thanks a lot, Bill Harwood. First, Kathy, I just want to echo Irene's comment. We realize, I think, that some anomalies are subjective in terms of how serious they might be. We understand that, but I think a lot of us would appreciate these more timely updates, so thank you very much. We appreciate that. Anyway, my question is for Gerst or Stitch. Could you remind us of what happens in landings with 3, 2, or even 1 chute inflated? I know you've told us this before, but I just want to make sure I understand that. And for Stitch, how is this different from and I say this with respect, what's been described in the past as the normalization of deviance. In other words, are you continuing to fly before you nail this down, are you accepting behavior that doesn't necessarily match what you expect from the design? And again, I say that with respect. Thanks.
Yeah. Thanks, Bill. I'll start with the first question. Going all the way back to the Apollo program, the parachute systems for human spaceflight were designed to tolerate a single chute out. And so what that means is for the SpaceX Dragon configuration, we could have one parachute totally almost be missing from the descent rate, right? So the way these systems work is the parachutes initially deploy and they reef to 2 different stages and then they fully open, and that slows the vehicle down. So you could have one parachute fully missing and still be certified to land. And we do extensive analysis for that configuration, and all that analysis shows the vehicle will be totally safe to land. So in this case, when we have one parachute lagging, it's essentially it is providing almost effectively the same amount of drag it needs to have that 4 parachute descent rate. So one parachute out, we're going to continue to dig into it, but it really doesn't affect landing performance very much. In terms of your last question relative to normalization of deviance, I would say we have probably more experience with these lagging parachutes than maybe we have shared with the media community. So I would say I'm looking at a chart right now that shows in previous tests we've had some parachutes that have lagged about 75 seconds or so in testing. So I would say this is within what we have seen in testing. So we are looking at the flight data, we're comparing it to our qualification testing, we're comparing it to other parachutes. What we are learning a little bit more about here is, the Dragon is the first vehicle that's flown with 4 parachutes. And so we're trying to understand, is there something unique about those 4 parachutes relative to the 3 parachute clusters we flew in the past, and we're just tracking that data very carefully. We are digging into this aggressively like we would any particular problem. We're trying to understand the physics, we're trying to understand what's going on, and so I think we're taking all the right steps in this investigation and looking at the data. So now I'll turn it over to Bill and see if he has anything to add.
Yeah, I'd just add that we're really certified for 3 chutes. The other thing I would add is that if you look at the actual descent velocity for this case, even though this chute is delayed, it still is providing significant amount of drag as you would expect from a normally fully deployed parachute. So if you look at the actual trace of the velocity, the descent velocity, it fits within the entire 4-chute thing. So it's not like the chute has failed or is not operating. The chute is still providing drag, but it's not inflating at the timing we would expect it to. And that's what we're curious about. Why is that? Is it, as Kathy described, is that a feature or of this design, or is this something else that's there? We didn't see it as maybe as much as we're seeing now, and we want to understand, is there something else there? So I would say we're being hungry and inquisitive, and we're trying to understand, even though this isn't a big problem to us in overall performance, is there something here that we should learn and understand that might change the way we do operations moving forward? And that's what we're trying to do. So there's really, if you look at it, if we didn't have the video, you wouldn't even know that this was occurring. If you just look at the digital data, you would not be able to detect any change in performance. So the system is operating correctly, but even though the system is operating correctly, we're not happy with that. We're going to keep looking and see if we can understand better how the system actually operates and understand where the weaknesses are in the system so we can have a safer system for crews moving forward.
Can they safely land with 2?
I mean, Bill, let me finish up. I actually feel like that's showing that they're not just accepting the deviance, right? I mean, if we would have just looked at the data, you would have said my system is nominal, but they're still hungry. And that's what we got to keep. We got to keep looking at the hardware to say, what do we understand the hardware? Even when from a reaction, from a performance standpoint, it may be operating within expected limits. But go ahead, you had a second question.
No, I was just wondering what happens if a second chute didn't inflate in time, or can a crew survive a 2-parachute landing? I know it's certified for 3, but could you survive 2? Thanks. That's all for me. Thanks.
Again, I would say that the thing that we've seen in developmental testing is when we've actually did some testing where we failed one chute to begin with, and it provided essentially no descent capability. What happens in that case is the vehicle's falling a little bit faster and the loading on the parachutes is a little bit higher, and we've seen no delays in the 3 chute cases. So we don't see this as a worsening condition. In fact, it's potentially a self-correcting condition. As the velocity increases a little bit, the dynamic pressure associated with inflation goes up. It's going to help ensure that these chutes inflate. So we think, again, we're going to confirm this, but our initial thinking is based on developmental testing that this is a self-limiting condition, and we're not going to get into this 2-chute or 2-chute and 2 lagging parachutes. We think the system will correct itself as that velocity goes up. It increases the inflation force that goes into the parachutes, and it helps ensure that they will be opened in a timely manner. But we're going to use this as a chance to confirm that and make doggone sure we're really right and we understand how the system really operates.
And we'll take our next question from Michael Sheets at CNBC.
Hi, guys. I think this question is also for Stitch and Gersimer. I appreciate you guys taking this teleconference after Jeff's great reporting on the subject. I want to key in specifically on this data because this is an issue that, as far as you guys are looking at it from a data perspective, is within a safe range, even with the lag. I'm curious as to how you define and quantify the range of that lag. What is a safe rate for the parachute to open at, whether that's something you measure in time or in maybe percentage of how open the canopy is? What is the ranges basically from top to bottom of what's safe versus unsafe?
Yeah, I'll take it and then see if Bill has anything to add. So as I said earlier, a safe landing is possible with only 3 parachutes. So almost imagine if you just take that 4th parachute and just take it off the vehicle. You could land safely based on all the testing we've done. We do a lot of drop testing out of aircraft and helicopters to measure those descent rates, and then a lot of analysis. So that is a safe landing. What we have here is a parachute that lags a little bit in full inflation, and so even when we see it in this unpressurized state where it's not fully full of air, that descent rate is almost nominal. And so what happens is that parachute, as it's streaming and trying to inflate, creates some drag, which is a force that slows the vehicle down, and so you see that descent rate almost the same as 4. And as Bill said, we're looking into this even more and trying to understand the physics in detail to make sure that we're flying safely. And today we were flying safely with these 4 parachutes. This is a phenomenon that we've seen before. We just want to dig into it a little bit more. So you could have one canopy totally missing and still have a safe landing within the landing parameters that the vehicle is designed for. And so what those are is the structure can handle that descent rate for one canopy fully missing. The loads on the crew are totally safe, and the forces that go into the crew at landing are totally safe if one parachute is fully missing. And so that's how we define that 3. That's how the vehicle is designed for that one shootout failure case.
I think that the key parameter is descent rate at actual splashdown. And then as Steve described, we can tolerate 3 chutes providing drag capability and still meet that descent rate at splashdown. And that's the key parameter that says we're within the design, the structural design capability of the vehicle or not, is that descent rate at landing. And we have, in these cases, we have tremendous margin to that. We don't even see hardly any deviation in descent rate, even at altitude. And as long as the chute fully inflates by the end, then it's going to ensure we're back in the range of where we are with the 4-chute descent rate, which is significantly different than the 3-chute descent rate.
It's almost like the fourth chute, the contingency, the fourth chute, because it's additional margin, it's not getting enough load on it to inflate, right, all the time. Which is why Gers was saying when you drop down to a 3-chute, they're fully loaded. So I know it's we're still understanding this 4-chute, but it may be this feature of this redundant, you know, I mean, we always want to have a design that covers for contingencies, and so we're learning how in this dynamic phase how that 4-chute not needing to be fully robust at that stage because we really are designing for a chute-out contingent case. There's an interaction there, but from a vehicle performance standpoint, because of that contingency, it's operating nominally.
I think my question specifically is on the scenario where you have a fourth chute failure and a third chute's lagging. So what's the range then that you can have that, the amount of time you can have that parachute lagging, that third chute, and it still be a safe splashdown?
Again, it's a function of how much drag that lagging parachute is adding to the reduction and descent velocity. And what we've seen is, in this case, these lagging chutes are still almost adding the same amount of drag as a fully inflated chute. So there's really not a concern, at least on the initial look at this data from where we are. So in the scenario in the case you described, is we think the dynamic loading pressure will actually force that third chute to open fully and provide full drag. It looks like from the data we're seeing now, even in the case you're postulating to me where we have the third one is lagging, I think it's still going to provide a significant amount of drag even in that lagging condition that it may be equivalent to full 3 chutes. We don't know that yet, but we're going to go work through that, try to answer those questions and understand how much ultimate margin we have. And is there anything we need to do that we can improve the situation to make things better and add more margin and more safety in the future? So what we're doing is we're really studying this. We're getting tremendous data. We're kind of pushing the state of the art in large ring sail parachute design and development. No one else has done this. We're sharing this data openly with other folks. This is a super chance for us to learn. I consider this thing almost a gift that we got on CRS-24, that we're going to get a chance to now have 2 sets of data that we can play against each other, improve our models, improve our knowledge, and actually make a much safer system for everyone using these large ring sail parachutes in the future.
And as a reminder, if we could keep reporters' questions to one at a time to make sure that we can get to as many reporters' questions as we can during today's call. And our next question will come to Marcia Dunn, the Associated Press.
Yes, hi, Steve. I think you said that the last crew splashed down the parachute lagged by about 70 seconds. Is that correct? And what was the exact lag in seconds for the latest supply run? And you also mentioned that other supply missions had actually seen the same phenomenon. How many other missions over what period of time? Thanks.
Yeah, I think the exact data was Crew-2 lagged about 75 seconds after peak load, and then on CRS-24 it was about 63 seconds or so, so it was about 15 seconds different. And then we'll have to go, I don't have all the data on the other flights, but we can go get that. There was some laggers on some of the other CRS flights before we upgraded the parachutes on the old Mark IIs, and we can get that for you, Marcia.
And Marcia, you got to be super careful with that data because we have various configurations of the parachutes. Some of those are a different design. They're a Mark II design. Some are Mark III designs. So you got to be super careful when you go look at that data and not try to connect data that is not relevant to each other.
I think my point was these are large ring cell parachutes, and they have this propensity to have a lagger. And again, what's happening, I think Bill said it really well, when you initially go to inflate the parachutes, your airspeed and velocity is fairly high, and so you're ingesting air into the mouth of the parachutes pretty rapidly. And so what we're seeing on this current Mark III design is 3 of those parachutes ingest that air relatively quickly. Now, that's what you want to happen. As they begin to ingest the air, they are reefed. In other words, we slowly pressurize the canopy, then we cut a reefing line that allows the parachute to pressurize even more fully. As that happens, the descent rate of the vehicle slows down, and if that one canopy is shaded a little bit, it doesn't have enough air, then that one canopy is starved a little bit for air, and then you have to wait until the air gets a little bit more dense, as Bill talked about, for that canopy to pressurize. And that's what we are seeing, is that that lagging canopy always pressurizes because of the physics. And what we're doing through this analysis of the data from CRS-24 is making sure that that is what's actually transpiring, is we'll always have that fourth chute pressurized, and that's what we've seen in all the testing. That's what we've seen in these 2 flights. We're just now, through this investigation and analysis, validating that.
And our next question is from Lauren Grush at The Verge.
Hi, thank you for taking my question. I'm wondering maybe what kind of changes or mitigation measures are even possible with the Crew-3 Dragon on orbit at this point, if you do decide that some changes need to be made to the system, or does it have to more or less land as is? Thanks.
Yeah, there's really no changes that we envision right now for the Crew-3 Dragon on orbit. Those parachutes are obviously packed and stored away. And right now we don't envision any changes for any other vehicles. As Bill talked about, if we learn something over time, we will go embark upon investigating whether we should make any modifications. But again, right now what we're seeing is this is something that's inherent to this large ring cell canopy parachute design, and in particular this 4-chute configuration where you're trying to pressurize 4 canopies to arrest the descent rate. And I'll see if Bill has anything to add.
No, I think we did a very thorough review after we saw the Crew-2 late deploy before we launched Crew-3, and we were 100% comfortable with launching Crew-3, that there were no modifications needed, or we would not have launched Crew-3. We didn't learn anything from this CRS-24 that changes any of that rationale. We're going to go back and double check to see if we can understand some more of the finer points of how these chutes operate and work. But it's not a safety concern. It's not an issue for the crew. There's no modifications required on orbit. This is more of a learning exercise of how we can improve our design and engineering understanding of parachute operation.
And our next question is going to go to Eric Berger at Ars Technica.
Hi, thanks for doing this. The more we can talk to you guys, obviously, the better. I think I know the answer to the first question about how concerned we should be about the parachute issue. Bill just talked about it being kind of a learning issue. But, you know, if Starliner were flying, would this be the kind of issue that might cause you to stand down Dragon and switch to Starliner for this increment? And then, you know, secondly, could this be an environmental issue rather than a hardware issue? Pressure, winds at that level, the atmosphere different between these flights? I don't know. Just wondering. Thank you.
Yeah, let's see. This is Steve Stitch. From my perspective, this would not be one of those kind of situations where we would stand down Flying Dragon and fly Starliner for the crewed flights. I think what we are seeing here is, and at my level and at Bill's level, we see it across the vehicle, right? You design a system, you go test that system. In this case, we can do very high fidelity parachute drop testing out of an aircraft or a helicopter and see the performance. You know, in flight, it's a little different. We are looking at the data very carefully from both Crew-2 and CRS-24. Interestingly, they were both, you know, in a colder time frame. I don't know if that has anything to do with it, but in terms of density, we're going to go look at all those kind of factors, wind speed, density. Is there anything that looks off nominal there that implicates these 2 flights versus the drop test that we had? We saw it in a couple of the drop tests where we, had a little bit of a lagging parachute as well. There's just a lot of variability in the parachutes in terms of and Bill talked about the reefing stages. They're cut with a pyrotechnic device. There's a little bit of timing differences in all those, and we'll go look at all that data to make sure that's all within what we did in qualification and as we move forward and close out the CRS-24 lagging parachute.
And I think we have time for one more quick question. We'll go to Chris Davenport from the Washington Post.
Thanks, guys. There's been some talk about sharing the data and what you learn going forward to make these systems safer for others as well. I'm just sort of curious how similar or different are the parachutes that are on Dragon to the ones used on Starliner and Orion? Thanks.
Yeah, I'll take the question. They are they're all these large ring cell parachutes. That's the kind of parachute system that you have to generate this kind of drag and required for these the large deceleration that you need. There is commonality between the Starliner and Orion parachutes. In fact, the Starliner parachutes were essentially derived from the Orion parachute design. Those parachutes also have a propensity to one of them at times to lag behind a bit. We've seen that in Orion testing as well. So there's commonality. We are sharing the data across this community in terms of, we learned that these large ring cell parachutes also have an asymmetry phenomenon where they don't always pressurize equally, and that pulls on some of these parachutes have 80 suspension lines that go around the circumference that attaches to one riser that then goes down to the structure of the spacecraft. And what we've learned in the asymmetry investigation during our development program for both Dragon and Starliner is there's a little bit of unequal pressurization that pulls on some suspension lines more. We've been sharing that data across the community. I do think, if I step back and look at what's happening here is if you go back to Apollo, that program was largely developed based on a test program. Now we're collecting data in a different manner. We have way better imagery. We can measure the loads on the parachutes way better, and now it's almost like a new generation of learning is happening with these large ring cell parachutes as we embark upon using them for human spaceflight.
And that's all the time we have for today's call. I will turn it over to Kathy Leaders for final closing comments.
So first of all, we set up this telecon to continue to carry on our conversations about our progress, and I hope the team that's been reviewing the data and assessing the data, Steve and Gers today gave several examples how we're continuing to review the hardware, look at the hardware, even when per the system specifications the hardware is delivering to the desired outcomes. But that doesn't mean we don't stop looking, right? This is a case where, with the parachutes, yes, the chute system actually delivered a descent rate that was within our certification bounds. But that doesn't mean that we don't continue to understand and be able to model the behavior of those systems, because that's through that understanding that continues to give us a robust understanding of how the system's operating. And then be able to, like we've talked about, be able to convey that to our other suppliers and our understanding for our future exploration systems. Very, very and we really appreciate SpaceX being so open with us and sharing all of their fleet insight across their whole fleet, because it helps us then gain that understanding, and as Joel talked about, continue to have us perform our important role of making sure that we're able to tell our international partners that we can, that we're protecting their crew members. So we'll continue these discussions, and we'll continue to convey data and have these conversations. I do want to finish up by saying, you know, there was a lot of discussion about investigations. When we're going to be conducting like a formal investigation, we'll try to do a better job of, you know, making sure that that in our wording we're letting you know when we're having, you know, formal mishap investigations or versus we tend to use the term generically investigation, and that's just us just assessing and doing our normal job of checking out the hardware. And so we'll try to be more careful going forward to make sure that we're really conveying to you where we are in the process and what we're doing in the process so that you have an understanding of the how we're looking at the different aspects of the hardware. But thank you all for coming on board, and Josh and the team for getting everybody together so quickly within a day. Appreciate it.
And thanks again for everyone joining. We'll have more on this important mission, so follow us on the Commercial Crew blog, the NASA website and social media, and NASA television. And you can learn more at nasa.gov/commercial crew. Thanks and have a good day.
This does conclude today's conference. You may disconnect at this time. Speakers, please stand by.